Hi friends, today we'll discuss about Turing machine and how to design Turing machine for a given language. We have seen the limitations of finite state machine and push down automata. Let us see how the capability is enhanced by adding the features of write back and traverse to and from by using Turing machine. Turing machine provides an ideal theoretical model of a computer. The Chern-Turing thesis states that any algorithmic procedure that can be carried out by a human being or a computer can also be carried out by a Turing machine. Turing machines are useful in several ways. As an automaton, the Turing machine accepts type 0 languages. It turns out to be a mathematical model of partial recursive functions. It is used to determine the undecidability of certain languages. And it is used to measure the space and time complexity of problems. Turing assumed that while computing, a person writes symbols on a one-dimensional paper which can be viewed as a tape divided into cells. One scans the cells one at a time and usually performs one of the three simple operations, namely writing a new symbol in the cell being currently scanned, moving to the cell left of the present cell, and moving to the cell right of the present cell. With these observations in mind, Turing proposed his computing machine. Finite state machine can be thought of as a finite control connected to a read-write head. A two-way infinite tape divided into a number of cells. Each cell can store only one symbol. Blank in a tape is a tape symbol, not an input symbol. Initially, the read-write head will be pointing to the leftmost cell that holds the input. The input to and the output from the finite state automaton are affected by the read-write head, which can examine one cell at a time. In one move, the machine examines the present symbol under the read-write head on the tape and the present state of an automaton to determine the new symbol to be written on the tape in the cell under the read-write head. Motion of the read-write head along the tape either towards the left or towards the right of the cell. Next state of the automaton and whether to halt or not. Remember that a Turing machine may utilize the tape cells beyond the input limits. The blank cell plays a significant role in the working of Turing machine. Turing machine halts in any situation for which a transition is not defined. It is possible that a Turing machine may not halt. So, it's the responsibility of the programmer to set it that Turing machine halts on all inputs. A Turing machine M is a 7-tuple, namely Q summation tau delta Q naught B F, where Q is a finite non-empty set of states. Tau is a finite non-empty set of tape symbols. B belongs to tau, which is a blank symbol. Summation is a non-empty set of input symbols and is a subset of tau, and blank does not belong to summation. Delta is a transition function mapping the current state and the current input symbol headed by the read-write head into the tape onto next state, change in the input symbol on the tape pointed by or headed by the tape, and D representing the direction of the read-write head movement, L representing move towards the left, or R representing to move towards the right of the current cell. Q0 belongs to Q is the initial state, and F subset of Q is the set of final states. Remember that the acceptability of a string is decided by the reachability from the initial state to some final state. So, the final states are also called the accepting states. And it is not necessary to define the delta transitions for all the elements of Q into tau. Turing machine can be described by employing instantaneous descriptions using move relations, transition table, and transition diagrams. Let us see each of them one by one. An instantaneous description of a Turing machine M is a string alpha, beta, gamma, where beta is the present state of M. The entire input string is split into alpha, gamma, where the first symbol of gamma is the current symbol A under the read-write head, and gamma has all the subsequent symbols of the input strings. And the string alpha is the substring of input string formed by all the symbols to the left of A. The ID is given as the left sequence A4, A1, A2, A1, A2, A2, present state Q3, symbol under the read-write head A1, and the right sequence A4, A2. Let us see one more example of writing the instantaneous description. B are the blank symbols in the tape. Current state is Q0 and the read-write head is pointing to the current input symbol A. So, A will be towards the right of Q0 and the leftmost non-blank symbols of A string is X and towards the right is Y, B. So the instantaneous description is given as X, Q0, A, Y, B. For constructing the ID, we simply insert the current state in the input string to the left of the symbol under the read-write head. And we observe that the blank symbol may occur as part of the left or right substring. In one move, the machine examines the present symbol and the present state. That is, the present symbol is A and the present state is Q0. Q0 A determines change in the state from Q0 to Q1, change in the input symbol pointed by the read-write head from A to X. So A is replaced as X and move towards the right. So the instantaneous description is given as Q0 AABB, Q0 AABB instantaneous description goes to X Q1 ABB. X Q1 A B B. So the description of moves by the IDs is very much useful to represent the processing of input strings. Representation by transition table. The definition of delta is given in the form of a table called transition table. If Q comma A is equals to gamma, alpha, beta, we write alpha, beta, gamma under row Q, column A. So, if we get alpha, beta, gamma in a table, it means that alpha is written in the current cell, beta gives the movement of the head towards the left or right, gamma determines the new state in which the Turing machine enters. For example, let us assume a Turing machine with 5 states Q0, Q1, Q2, Q3, Q4, where initial state is Q0 and final state is Q4, with the tape symbols A, B, X, Y and blank. So let us see how to make a transition table entry for one single transition. Q0A is equals to Q1XR. So at row Q0 and column A, that is Q0A, at this position we go for writing XRQ1. XRQ1, where X represents the change of the symbol pointed by the read-write head in the tape, direction of movement of the read-write head left or right, next state or change in the state. So this is how we go for representing for one single transition in the transition table. Similarly for all other. Representation by transition diagram, where the states are represented by vertices. Directed edges are used to represent transition of states. Labels are the triplets of the form alpha, beta, gamma, where alpha and beta belongs to tau and gamma belongs to left or right. When there is a directed edge from Qi to Qj with the label alpha, beta, gamma, it means that delta of Qi alpha is equals to Qj beta gamma. So let us see part of a transition diagram for the delta transition. Q0A goes to Q1XR. So the current state is Q0 going to new state Q1 for input symbol A, wherein the input symbol A is replaced by X and the read-write head is moved towards the right. So this is how we go for representing the transition diagram. It is same as that of your finite state machines and push-down automatas. The label for each transition will be current input symbol, change in the input symbol, and the direction of the read-write head movement. For example, for the language A raised to n, B raised to n, the computation sequence for the Turing machine for processing the input string AAA BBB is represented by multiple instantaneous descriptions, starting with the initial state pointing to the input string. With multiple instances, it reaches to the instantaneous description XXX YYY blank Q4 blank, where Q4 is the final state, and hence the string A raised to 3 B raised to 3 is accepted by the Turing machine. When do we say that the language is acceptable by the Turing machine? Consider the Turing machine M is equals to Q summation tau delta Q naught BF. A string W in summation star is said to be accepted by M if initial state Q naught for the input string W for multiple instantaneous descriptions reaches alpha 1 P alpha 2, where alpha 1 and alpha 2 are tape symbols and P is a final state. M does not accept W if the machine M either halts in a non-accepting state or does not halt. For example, as we had seen in the previous slide, for the language A raised to n, B raised to n, starting with the instantaneous description, initial state Q naught pointing to 3A's and 3B's with multiple instances reaches XXX, YYY, blank, Q4 blank, where Q4 is the final state. Hence, the string AAA, BBB is accepted by the Turing machine. Before designing a Turing machine for a given language, let us go through the basic guidelines. The fundamental objective in scanning a symbol by the read-write head is to know what to do in the future. The machine must remember the past symbols scanned. The Turing machine can remember this by going to the next unique state. The number of states must be minimized. This can be achieved by changing the states only when there is a change in the written symbol or when there is a change in the movement of the read-write head. Let us design a Turing machine that accepts a language L is equals to A raised to n, B raised to n, where n is greater than or equal to 1. We construct a Turing machine M as M is equals to Q summation tau delta Q naught BF, where many of the things we don't know, they are blank. Summation is AB. Rest all values will be filled once we complete designing the Turing machine for this particular language. In pushdown automata, we could keep track of the number of A's equal to number of B's by pushing A's into the stack and popping the topmost element of A when the input string has a B. Whereas in the Turing machine, we have a tape, and the logic behind designing the Turing machine that accepts the language A raised to n, B raised to n is, for example, if I have 3 A's and 3 B's, find the leftmost A and replace it as X. Move towards the right, find the leftmost B, replace it as Y. Again, then go back. Again, find the leftmost A, replace it as X, and then leftmost B as Y. So, in this way, we have to complete the cycle. Again, go back to the left, replace A by X and B by Y. And now we are left with only X and Y. Hence, the number of A's are equal to number of B's. So, let us see the tape in the Turing machine. Here is a tape which is two-way extended. Okay, and we have stored the input string as A, B, B, and before and after in all the cells we will be having the blank symbols, and your read-write head will be pointing to the first leftmost symbol in the input tape. So according to the logic discussed, find the leftmost A, replace it as X, move towards the right until you find the leftmost B. Once obtained, replace it as Y and go back left until I come across first A. When do I come to know that it is a first A? Go on moving until I get the first X and just move towards its right. So that will be your leftmost A. So this completes one cycle. So again, replace A by X, move towards the right to find the leftmost B, replace it by Y and go back left until I come across leftmost A. So leftmost A is obtained until we come across a X. Once we come across a X, move towards the right. That will be your leftmost A. This completes the second cycle. Similarly, we have to repeat the third cycle. A is replaced as X and B is replaced as Y. Then come back until towards the left until we come across the first X. So once we come across the first X, move towards the right, which must be your first A. But right now you see here it is a Y. It means all A's are exhausted. If so, then in future towards the right, I must not come across any B. If I come across any B, it means the number of B's are greater than number of A's. So in future, I must get only Y's. And after all the Y's, if I come across a blank symbol, then I must reach an accepting state. So this is the simple logic of designing a Turing machine to accept the language A raised to n, B raised to n, where n is greater than or equal to 1. So till now we just discussed about the logic, whereas we have not yet discussed when to change the states. So to make you more understandable, I have changed the color of the read-write head along with the states. So let us see when to change the states. Initially, the read-write head is pointing to the first leftmost symbol, that is A, and it is in the initial state Q0. So once it is in the initial state and finds the leftmost A, then the first step is replace A by X, change the state from Q0 to Q1 and move towards the right and keep all the things as it is or input symbols as it is in the tape until I come across the first leftmost B. So you can see here Q1A. So A is kept as it is, move towards the right, be in the same state. Again, move towards the right, keep the same state as it is. Next, now you can see here when you are in Q1 state and it is pointing to the first leftmost B, then change this B to Y. So for 1A is replaced as X, for that 1B is replaced as Y. So once that is done, then change the state and go back. Till what time we have to go back? As I said, until I come across first leftmost X, I must go back and be in the same state. So I'm at state Q2, keep things as it is. So next Q2A, keep A as it is, move towards the left until I get a X. So here you can see I'm at state Q2, I have got X. It means what? Towards its right, I will be having the leftmost A. So here completes one cycle and then again it will go back into the initial state. That is Q0. Again, Q0 leftmost symbol is A. Then again replace A by X. Change the state from Q0 to Q1. Move towards the right, keeping the input symbols in the tape as it is until we come across the leftmost B. Q1A. Is it a B? No. Keep A as it is, B in the same state, move towards the right. Q1Y. Is it a B? No. Keep the symbol Y as it is, move towards the right, B in the same state, Q1. Again, Q1B. Then what to do? Replace B as Y as it is the leftmost B. Change the state and move back in the left. So now the state is changed back from Q1 to Q2. And now we'll be going on moving in the left until we come across the first X. Q2Y, keep Y as it is, move towards the left. Q2A, keep A as it is, move towards the left until I get a X. So once I get a X, here completes the second cycle, move towards the right and change the state to initial state. So now again we are entering into the second cycle, that is initial state is pointing to the first input symbol A or the leftmost A. Replace it by X, change the state to Q1, move towards the right until we come across leftmost B. Once we get, replace B by Y, move towards the left, change the state. Be in this state Q2 until we get the first X. So now once we got a X, so according to the rule, change the state to initial state, move towards the right. Now, at this state, it is in Q0. If we had one more A, then again we'll be having one more cycle of A replacing as X and B replacing as Y. But right now, at this situation, when we come across a Y symbol at the initial state, then go on moving towards the right until we come across a Y. And now here we have changed the state. Again, keep Y as it is, move towards the right, be in the same state. So again, move towards the right, be in the same state, Q3. Once you are in state Q3 and you have come across a blank, it means number of A's are equal to number of B's. Hence, change the state from Q3 to Q4, which wherein Q4 is the final state, and you can move either towards the left or right. Since you have reached the final state Q4, the string is accepted. So this is how we go for changing the states when needed. I hope you understood to design the Turing machine for this particular language. So next we are supposed to write the delta transitions. Q0A, the first delta transition is when you come across Q0A, change the state from Q0 to Q1, A is replaced as X and move towards the right. Next, once this is done, when you come across Q1A, keep A as it is, be in the same state and just move towards the right. So for that, we have the second rule, Q1A, keep Q1A as it is, just move towards the right. Next, Q1A, already we have the second delta transition for it. Next, when we come across Q1B, what to do? Change the state from Q1 to Q2, replace B by Y and move towards the left. Next, in the left, we came across Q2A. So Q2A, keep Q2 as it is, A as it is and just move towards the left. Q2A, already we have fifth transition for it. Next, go for Q2X. So when we come across Q2X, what to do? Q2 is changed back to Q0 as it completes one cycle. Keep X as it is, move towards the right. So once change the state from Q2 to Q0 and move towards the right. So this completes one cycle. with the delta transitions 1, 2, 3, 5 and 6. Next again Q0A. So Q0A means Q1 A is replaced as X, move towards the right. Next Q1A. So for Q1A, Q1 as it is, A as it is, move towards the right. Next Q1Y. We don't have any transition here. So let us write one more transition. Q1Y. So Q1 as it is, Y as it is, move towards the right. Next Q1B. So Q1B. So this is your first leftmost B. Replace it by Y. Change the state from Q1 to Q2 and move towards the left. Next Q2Y. We don't have any transition for Q2Y. So let us write one more transition. Q2Y. What to do? Be in the same state. Keep Y as it is and move towards the left. Next Q2A. Again keep everything as it is and just move towards the left. Coming to Q2X. Q2X here completes the first cycle. Second cycle again start with a new cycle by replacing Q2 by Q0 and move towards the right. Next again Q0A. A is replaced as X. Q0 is replaced as Q1. Move towards the right. Q1Y. Keep as it is. Move towards the right. Q1B. Q1 is replaced as Q2. B is replaced as Y. Move towards the left. So next Q2Y. Q2Y keep as it is. Go on moving towards the left until you come across a X. So once we come across a X, so Q2 is replaced as Q0. Keep X as it is. Move towards the right. Now at Q0 we don't have A. We have a Y. So at that time we will change the state from Q0 to a new state, that is Q3. Move towards the right, keeping Y as it is. And henceforth, until we come across a blank, we must come across Y in state Q3, for which we write one more rule. In state Q3, Y, be in the same state, keep Y as it is, just move towards the right. Q3Y, Q3Y, just move towards the right. So once we come across Q3 and the input symbol is a blank, that is the tape symbol is blank, then go to a new state which is a final state. Keep blank as it is and either you can move towards the right or you can move towards the left. So once the input is consumed, you have reached the final state. Whatever is the tape symbol, the string AAA BBB is accepted. So these are the 10 delta transitions written in order to design the Turing machine. Once we have obtained the delta transitions, we can represent the transition diagram. So let us see how to represent the transition diagram for this particular language. So first delta transition is Q0A going to Q1XR. So Q0 is the initial state having a transition to Q1 where for A is replaced as X, move towards the right. So on the transition, you'll be having the current input, change in the input symbol on the tape and the direction of the movement. Next, Q1A, it will go into the self loop AAR. Q1Y, again a self loop, Q1Y goes to Q1 where Y is kept as it is, Y is kept as it is and move towards the right. Similarly, Q1B, it will go to the new state, Q2, B Y, L. Next transition, Q2A, a self loop, A, L. Q2X, so from Q2 for X, it is going to Q0. So from Q2, we'll be having a transition to Q0, wherein X is kept as it is and move towards the right. Q2Y, again will take a self loop. Q0Y will go to a new state, Q3, where Y is kept as it is. Y is kept as it is and move towards the right. From Q3, a self loop for input symbol Y and move towards the right. And finally, from Q3, a transition will go to Q4, where Q4 is a final state where the blank is kept as it is, and you can, as I said, you can move towards the left or towards the right. Since Q4 belongs to F, the string is accepted. So this is the transition diagram for the given Turing machine. Once we have written the delta transitions and transition diagram, the same can also be represented in a form of a transition table. So let us see how to represent the transition table for this particular language. So in this language, we have come across 5 states, Q0, Q1, Q2, Q3, Q4, where Q0 is the initial state and Q4 is the final states. Then coming to the tape symbols. So here the tape symbols are A and B initially stored. Then A is replaced as X and B is replaced as Y. So XY will be the tape symbols. And finally B. So as you must not have confusion in between this B and this B, so I have taken the blank symbol as capital B. So we have the 5 tape symbols. Coming to the delta transitions. So first delta transition is Q0A. At Q0A at this location, we will be having X R Q1. So X represents the change in the input symbol in the tape, direction of movement right or left, and change in the state. Q0Y. Q0Y is equals to YRQ3. YRQ3. Next, Q1A. Q1A is ARQ1. Next, Q1B. Q1B here. It will be YLQ2. Similarly for all the other transitions. Q1Y will be having YRY, YRQ1. Q2A will be having ALQ2. Q2X as XRQ0. Q2Y at this location YLQ2. Q3Y will be having YRQ3. And finally Q3 blank at this location blank RQ4. So this is how we go for representing the delta transitions in the form of transition table. So once we have designed the Turing machine for the given language, we have written the delta transitions, transition diagram, transition table. Next is to check whether the given string is accepted by this particular Turing machine or not. So we have taken the same string A, B, B, B pointed by the initial state Q0. Then first step is replace A by X, change the state, move towards the right. And we have discussed already how to write the instantaneous description. So the current instantaneous description will be X Q1A B, B, B. Then move towards the right. So the next instantaneous description is X, A, Q1, A, B, B, B. Similarly, next instantaneous description is X, A, A, Q1, B, B, B. And in this way, the instantaneous descriptions will be derived until we reach the final state. So these are the intermediate instantaneous descriptions, and finally once all the A's are replaced as X and B's by Y, it will go on moving towards the right, and finally it reaches the final state Q4, and the tape symbols are X, 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 Y, Y, Y. Q4 is the final state, hence the string AAA BBB is accepted by this Turing machine. The complete design of a Turing machine that accepts the language L is equals to A raised to n B raised to n, where n is greater than or equal to 1, is M is equals to Q summation tau delta Q naught BF, where Q consists of 5 states Q0, Q1, Q2, Q3, Q4. Summation is AB. Tau is AB, X, Y and blank. Final state is Q4 and initial state is Q0. Blank symbol is represented by B with 10 delta transitions represented in the form of a transition table and transition diagram. This is how we go for designing the Turing machine. Few more Turing machines will design in the next lecture. Thank you.